Okay, so today we will review the Pytorch library. Okay, so far we learned about OpenCV library and also the deep learning. Okay, and this Pytorch is the Python library that may help us to implement deep learning algorithms. Okay, it's not that difficult. Actually, they try hard. Actually, this Pytorch is developed by Meta, previously the Facebook, and they try hard to make this implementation easy. Okay, so it's very easy to use. Okay, so this is the architecture we learned last time. So we say we have to define three things when implementing each layer. Okay, the forward rule. This is the rule for go from left to right. So we have defined some function, right? So input is x, some input is x, and for given layer f, there's input and output, right? Input x and output y. And also there are some parameters sector, right? So our function f need to be implemented to output some output y from the given input x and the parameter sector. Okay, and also the operation that connect this input x and parameter sector should be differentiable. Okay. And this backward rule and the parameter update rule have to be defined to be used as the intermediate layers in the deep learning. Okay, so the backward rule is defined as this. So the differentiation of output y respect to their input. This is the backward rule, and the parameter update rule is the differentiation of the output y respect to the parameter sector. Okay, so we need these two gradient for each layer. But exceptionally for this parameter update rule, if the layers do not have any parameters, then we don't have to define this parameter update rule for that layer. Okay, but this backward rule, we have to define this for every layers. Okay, and we have to define this parameter update rule for layers that have parameters. Okay, this is required to calculate this gradient descent formula, right? Okay, and the Pytorch, I mean, if you do not use any deep learning library such as Pytorch, you have to define this kind of three things by yourself in Python. But one good thing when you use the deep learning libraries, such as Pytorch, is you don't have to implement this gradient calculation by yourself. Okay, that's the important thing in Pytorch. Instead of if you do not use Pytorch, you have to define, for example, let's say your parameter update rule looks like this. Then you have to calculate their dy dx by yourself. This might be applying d dx to both sides, right? And the left side would become like this, and the right side would become like this, right? And you have to implement this in your layer implementation. And also you have to calculate this as well. dy dissector might be like this. And you have to implement this by yourself in the layers, okay? But a bad thing is this gradient, their formula always changes as the forward rule changes, okay? So for each layer, if their forward rule is different, you have to define their respective backward and parameter update rules by yourself in the code, right? This is not convenient. And also sometimes it is hard to implement this gradient because it is hard to obtain the, how to differentiate some function, right? So, and also there's some, sometimes the function is not differentiable. I mean, they are differentiable, but it is hard to obtain their gradient by hand, maybe, okay? There's some cases like that. So this has many disadvantages. So people feel that implementing this backward and parameter update rule involving the gradient terms are not easy, right? But if you use Pytorch library, you don't have to care about calculating this gradient, okay? The library automatically learns, automatically calculate all the gradient in the numerical way, okay? So so even for some functions that does not have any closed form formula like this, you can calculate the gradient because this library can calculate such gradient in the numerical way. Somehow they approximate. So for some difficult functions that is hard to obtain the gradient, you can calculate, okay? And also, another good thing is, I said that in this way, if the forward function changes, you have to calculate the backward rule and parameter update rules by yourself again, right? For each different forward rule. But if you define this algorithm, the calculation of gradient in the numerical way, that's same for all the functions. Okay, that's kind of algorithm, and that is invariant to the forward rule. So maybe in calculus, you already learned about some Newton method like that. So some method that iteratively approximate the gradient, okay? So if we implement such algorithm once, that algorithm itself is not changed depending on the forward function, right? So we do not have to implement this forward rule and this parameter update rule method depending on the forward rule, okay? That's another good thing, okay? So the only thing we have to do is calling these two functions when calculating the gradient and when calculating this gradient descent, okay? So we will see that again in the later slide. So I will first explain you how to use this Pytorch given some simple example, implementing the linear regression algorithm, okay? So I assume that you are already familiar with this linear regression, but for some who are not familiar with this, I will give you very brief explanation about this. So linear regression is the regression algorithm, right? And in regression, we have to estimate the output y. This is the output, and this is the input, okay? So we have to we have to estimate output, continuous value, output y, from the continuous input x, okay? That's the regression task. And also we will achieve this using only the linear function, okay? That's linear regression, okay? We will do regression that finds the continuous output from the continuous input. But we will do that using only linear operation. That's linear regression. And because we will use the linear operation, the input X and input Y, they will be related using two parameters, the weight W and some bias B. We normally call this as weight and this is bias, okay? So this is something you learned in high school, right? This is the linear equation, right? But one different thing is this X and Y could have multi-dimension in this example, right? Anyways, so actually these blue dots, blue points, they are the training samples. This is a blue point. They are training samples. Right. So actually they are, in this example, this have just one value. This is not not vector yet, and this is also not vector yet, having just one value and one value. You can imagine that this is kind of weight of the person, and this could be some height of the person, because there are some of the linear relationship between weight and height of the person, right? Maybe we can exemplify this as the finding the height from the person's weight. Okay, we can assume like that. Okay, and these blue points that are indicating each person's maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We are given 10 persons weight and height data, right? Then we can visualize it in this two-dimensional graph. Okay. And the thing we have to do is to find this regression line. Okay. And actually, this line is linear equation, and finding this regression line is equivalent to finding the W and B, right? And we will find it from this, given these 10 training samples, we will find this regression line that minimize these errors. So, I mean, this straight line is meaning that when this weight is given, their height would be estimated to this height, right? But the real samples will have this height, so this gap is the error, right? We will predict the height as this, but the real sample's height might be here, and these two are kind of the loss, okay? The loss is the distance between ground truth and our prediction, okay? So we will minimize this gap, which is the loss, and for the straight line that can minimize this loss would be selected, okay? This is the linear regression algorithm, okay? Are you guys following this? Okay. And actually, we will implement this code is the example implementation of this linear regression algorithm using the Pytorch, okay? This is very simple. So this upper code, maybe the 7 lines of code, 8 lines of code, they are indicating making some data, okay? So for making data, we have to define the ground truth W and ground truth bias first to sample data from this line. And also, this is the W and B. This is the initialization for the matrix W and B. So we will update this randomly initialized W and B to be close to this WGT and BGT, okay? So anyways, we randomly initialize. This is the random initialization. And also for X, for maybe for weight data, this input, we will randomly generate it for 100 samples, okay? And this time, the input has 3 dimensions. Okay? In this implementation, we implemented to have 3 dimensions for the input, okay? And this Y is sampled from this ground truth W and ground truth B, and we multiply the randomly generated input to that to make some data Y, okay? So this first part is the data generation part, okay? And here, what we do is we iteratively apply the gradient descent on randomly initialized W and B parameter, okay? So we have to, from the randomly initial values, this W and B need to be close to the ground truth W and ground truth B, right? And we will iteratively do this, maybe for 100 iteration. And at first, we have to initialize our gradient. So this W and B is the Pytorch variable, and it have two instant variable. So the first one is data, and the second one is grad. Okay, this one also have data and grad. This data is indicating the value this variable is having. Okay, and this grad is indicating the gradient value for this W. Okay, so actually this is actually indicating this DLDB, and this is also indicating this DLDW. Okay, this dot graph is indicating the differentiation of the loss respect to that variable. Okay, but at the initial step, we have to initialize it as known. Okay, and we will define the forward function. Okay, so we will multiply X, the input variable, with the W, and also we will add bias B to predict Y. Okay. Okay, this is our forward rule, right? We have to define that. And then we will define the loss function. Okay, the loss will measure the difference between predicted value and the ground truth. Okay, we will calculate that using the Euclidean distance. Okay, so this loss is indicating that, right? And then what we do is we will call loss dot backward function. Okay. As I mentioned, if you do not use Pytorch, at this step, what you have to do is calculating this DLDW and DLDB by yourself. But because you are using the Pytorch library, you don't have to do that. Instead, the thing you have to do is just calling this loss dot backward. Okay. Then inside the Pytorch, it makes some graph, and the graph maybe you saw in the last time. I explained how computers are calculating the gradient in the graph, right? So somehow using this formula, it makes some graph inside the Pytorch library and calculate the DL dissector for all the parameters. Okay, that's happened inside the Pytorch when you call this loss.backward. Okay, and this is the gradient descent formula, right? And this is appending some rules for visualization purpose. So this iteratively happens, okay? And the W is iteratively updated here to be close to the ground truth W and ground truth B, okay? Are you guys understand this? Okay. So anyway, if you, after the iteration, if you plot the obtained W and true W, and also the obtained B and true B, then the result would be like this. So the ground truth was 1, 2, 3, then your predicted W and predicted B would be same as their ground truth values, okay? And this is the visualization for loss. This is the iteration, and this is the loss. So loss is the distance between predicted value and ground truth value. So at the first iteration, it is very high, but you can see it is gradually reduced after the iteration goes, okay? So you can see this gradient descent is indeed working, right? Okay. But more important thing is here. So if you want to implement this linear regression algorithm, so maybe these 2 slides are added, maybe this afternoon. So maybe some of you don't have that, right? I'm not sure, but some of you have that anyways. Anyway, so if you want to implement this linear regression algorithm using the NumPy library, which is the Python library that can deal with the multidimensional array. If you want to implement this NumPy, which is not deep learning library, the thing is like this. So here you have to make the data by yourself. But different thing is here, maybe you have to calculate this gradient by yourself. Okay. Instead of calling the backward function, you have to define these gradient values by yourself. Okay. But this is not convenient because if your forward rule is changed, you have to define this every time. Okay. And for some difficult functions, you cannot even calculate this, right? Anyways, but when using the Pytorch library, if you just calculate if you explicitly say about your forward function, then inside the Pytorch, they generate some graph. And if you call the backward function, then the gradient are calculated for every parameters that are inside the graph. Okay. So you don't have to care about the gradient calculation. Okay. So this is the different thing between NumPy implementation and this is the Pytorch implementation. This is quite easier, right, than calculating every gradient. Okay. Are you guys understanding this? Right. Any questions? Okay. So this is the example of the graph, which is constructed inside the Pytorch. Okay. So if you somehow, if you define some functions like this that connect the intermediate variables to output the final output y. This is called as final output because they are used in loss calculation. Okay. Anyways, if you explicitly define the functions like this, then inside the Pytorch, they generate graphs like this, okay, automatically. So they actually connect variables via some operations like this to generate the output here, okay? And if you call the load stop backwards, then every variable which is connected to these loss functions are assigned with gradient value, okay? Okay, so this is the Pytorch library. Okay, so load stop backward, this is very powerful tool, okay, when implementing deep learning architecture, because this is the simple algorithm. Linear regression is relatively simple algorithm, which does not have many parameters. But in deep architectures, there are a lot of parameters. So you cannot manage every parameters by yourself, okay? But when you have this kind of Pytorch library, the management for each parameters become very easy. Okay? And from now on, I will explain the Pytorch style code. Okay, so I mean, these two codes are both the code written for using the Pytorch library, but these right things are more simple. Okay, so anyways, I will explain you first. So for some of the frequently used operation, the Pytorch is already defined them in their this torch.nn package. Okay, so this wx plus b operation is called as linear operation, and actually this is quite frequently used in implementing the deep learning architecture. So they already implement this layer inside the torch.nn package. Okay, so you can define their parameters by yourself in this way, but more elegant way of defining how to say this kind of architecture is to use this torch.nn linear layer, this kind of function. Okay, it's more elegant way, but their functions are same. Okay, the thing which is good when you define your architecture using this kind of way is you don't have to specify their detailed operations. Okay, I mean, here you have to initialize W and B, and also you have to define the linear operation, linear formula by yourself. But here, because you already implement the linear operation is already implemented in Pytorch. So the thing you have to do is just define some variable net using by defining it using the linear layer. And the thing you have to do here is just input x variable to the net architecture. Okay. So the implementation becomes slightly easier, right? But I recommend this especially when you implement the deep architectures, because deep architectures have a lot of parameters, right? So sometimes you cannot define that deep architecture in this way, okay? Because there are a lot of parameters, a lot of formulas inside, right? But this kind of the layer definition makes you a lot easier to implement big architectures. Okay. And this is not that important thing, just squeezing some dimension, right? This is for this kind of thing, changing this to this kind of. So squeezing is just removing this one-dimensional axis. Okay. So because this is not actually 3D array, actually the 2D array. So squeezing is removing this kind of things. Okay. Okay. And next thing is this. So previously we can also define this kind of operation by ourselves. Okay, but this kind of operation also could be simplified. Okay, so the Pytorch library in torch.optimization package, they already define several gradient descent algorithms. Okay, the SGD, this is the stochastic gradient descent algorithm, which is the simplest version of the gradient descent. And yeah, that's actually formula looks like this. And they are already having this kind of gradient descent formula. So you can write it like this, but more easy setting is to call this torch.optim.sgd function and to make this optimizer variable. Okay, and you have to specify two things inside this function, which is the list of parameters for the net architecture you defined. So this is actually W and B. So if you call net.parameters, then the parameters you have in net variable is returned. So actually this is the W and B, right? This is the parameters we will learn, okay? And the next thing is the learning rate. And actually this learning rate is this small scala value, okay? So, I mean, this is the gradient descent rule. So you will update this old parameter W to the direction of gradient with some small scale, right? And this small scale is usually like this, some values less than 1. And that value is actually initialized here as the gamma variable. So you have to define this LR when defining the optimizer. So when before actually doing this, you have to define. You have to define this epsilon value and also this W old. You have to register this and this in optimizer. Okay. And the thing you have to do is calculating DLDW, right? And actually doing this once. Okay. If you do that, the W parameters we want to learn is updated, right? So in optimizer, when defining optimizer, we give these two information. And in this for loop, what we do is we initialize our gradient. Okay. So previously, what we have to do is implementing these two lines by initializing every gradient of the all parameters. But if the parameter numbers are becoming larger, for this, even you take a lot of lines, okay, when implementing the code. So, but if you manage the parameters using this optimizer, the thing you have to do is just calling this one line of code, okay? If you call optimizer.0_grad, then for every parameters registered here, their gradient becomes known, okay? And you define the forward rule and calculate the loss and call the loss step backward. Then these gradients are calculated, right? And next, the thing you have to do is indeed calculate these ones to update the parameters. And that also can be implemented with one line of code, optimizer.step. Okay. So these two code, load step backward and optimizer.step are important. So when you call load step backward, these gradients are for all the parameters are calculated. And if you call this optimizer.step, this is calculated for every parameters, okay? Okay, this is maybe the highlight in Pytorch. And another thing is, even for loss function, sometimes implementing this loss function needs some technique to manage their dimensions, okay? And sometimes it is, anyways, tedious, not convenient to implement this kind of loss function by ourselves. So in Pytorch, the loss functions are also already implemented in pytorch.nn package. So this is the MSE loss already implemented. So this is called as Euclidean distance or L2 loss or MSE mean square error loss. It have a lot of name, but this is selected for here. So if you call torch.nn.msc loss, this loss underbar fn is actually the definition for this MSC, becomes the definition of the MSC loss. And the thing you have to do is just inputting the ground truth and the predicted value to calculate the loss, okay? So this is more convenient way to implement, to use the Pytorch, okay? And anyways, the results are same as before, okay? So in Pytorch code, the flows are like this. So we first define some data and define network and define optimizer and define loss. And in the for loop, for each iteration, we initialize gradient and define forward, calculate loss, and do loss backward, and update the network parameter. Okay. This is the flow happen in the Pytorch code. Okay, and the real code looks like this. And actually, the for loop here, initializing the gradient and doing the forward and calculating the loss and loss step backward and optimizer.step. These are maybe not changed for other architectures, depending on the architectures. The merit of this Pytorch style code is actually that thing. So even though other, so various architectures could be here, but this core code that actually does the training will not be changed much, okay? That's the merit of Pytorch style code. The thing you have to change is only this part. You have to sometimes change the architecture, your architecture, you have to define by yourself. And also you have to sometimes change the optimizer by changing it to more advanced algorithm, right? And also you have to also change the loss function depending on the application. Okay, but this for loop may not be changed much. Okay, and also you have to define your data by yourself. Anyways, that happens outside of this for loop, actually the training code, but inside this for loop, the code will not be changed much. Okay. Any questions till here? Okay. No. And the next thing is more advanced architecture, the called as multi-layer perceptron. So this architecture is having stacks of, you can roughly think this as having like this. So stacks of linear regressor is actually multi-layer perceptron. So I mean, linear regressor, their operation was like this, multiplying some W and adding some bias. This is the linear regression operation. But in multi-layer perceptron, you will stack this WX plus B maybe in more than 2 layers. Okay. If you stack multiple linear regressor, then it is called as multi-layer perceptron, which is the MLP. Okay. So actually, this is the example of the multi-layer perceptron. Okay. So here, the initial input is multiplied with first layers W and B, and then multiplied with second layers W2 and added with the bias 2, right? And then third layers operations are done here, okay, to output the final output. Okay, this is the MLP, right? And we will implement this structure using the Pytorch library from now. Okay. But here I will explain why this sigma, the nonlinear functions, are required. Okay. So maybe if there's no nonlinear function here, then yeah, that formula looks like this, right? Maybe. And if you simplify this equation, then you will get this kind of formula, right? But this becomes, again, the linear function, okay? If you do not use any sigma, the nonlinear layer in between the linear layers, the formula may become like this, and it could be simplified as the simple linear regression, okay? So the huge network that does not involve any nonlinear operation inside may converge to a simple linear regression task, a simple linear regression architecture, okay? So actually, this is the reason why you have to involve these nonlinear layers in between the linear layers, okay, to give some nonlinearity, okay? And this is the implementation of this MLP using Pytorch. And you can feel that there are some data generation part here. And this part is same as before. The training part, they are same as before. And the loss and optimizer, they are also same as before. And the thing you have to change is this part, the definition of the architecture. Okay. Previously, we used just one layer, torch.nn.linear, right? Because it was the linear regressor, right? But here you can see, actually this torch.nn.sequential, this function is for stacking multiple layers inside this parenthesis, okay? So actually this architecture is defined to stack multiple linear and ReLU layers, okay, in sequential way, okay. And the data we define is for X, the input, we randomly initialize it, and we will use 1,000 data. And the Y, it may have some nonlinear operation like this. This is the data we will make. Okay, we will make 1,000 data that have this kind of relationship between input and output. Okay. So if you code this, execute this code, then in this for loop, we will find some appropriate net architecture that mimics this original formula. Okay, but we cannot find exactly this same formula, right? Differently to linear regressor, we actually define the same form of parameters with the ground truth linear equation. For this nonlinear function, we cannot do that actually, but we enforce this kind of MLP architecture to mimic this function, okay, this time. And actually, after the training ends, you can see this kind of result. So we can print, this is the ground truth for random access. This is the predicted values from our learned architecture. So we can somehow print out these Y values here, right? But maybe because it's not the exact function, so the values could be different in small scale, but the roughly, you can see they are mimicking the original function, okay? Anyway, the networks are long, okay? But important thing here is, again, using this kind of Pytorch code, the thing you have to change is this part, the network architecture and the loss functions and optimizers, okay? And also the data part, okay? So now you can, kind of deep architectures using the Pytorch library, okay? This is very short code, right? But you can train any kind of architectures, okay? And till now, we implemented the simple linear regressor and also the MLPs, right? Using Pytorch, okay? But from now on, I will introduce you how to implement this convolutional neural network, okay, using Pytorch. Because it is different from MLPs in the fact that it is involving some convolution layers, okay? But in the fully connected layer, I already explained this. These fully connected layers are actually equivalent to MLP layers. So in the first part, because the signals are 2D, two-dimension, we have to apply convolutions to process that, right? But we tend to gradually reduce the 2D signal towards the 1D signal here, okay? And after some time, we flatten 2D signal to 1D and then apply fully connected layers. But these fully connected layers are actually equivalent to MLP layers. Okay? So actually, this could be implemented in Torch.NN and then the linear operation. And also in Pytorch, there are already conv layers. So in the former part, you will implement each layer using this function. And the later layer that process the 1D signal, you can implement them using this linear function, okay? So, and I have to also explain this. So previously in net, when you define this net variable, we define it like this, okay? But if you make them as the class, it's more convenient and it provides a powerful, some merit, okay, compared to the previous definition. So actually, the class here is indicating the deep architecture, and we are actually inherit this torch.nn module, okay? But besides that, this class is actually having the same characteristic with the standard class in the Python, okay? So maybe I assume that most of you are familiar with OOP, the object-oriented programming. Inside that, we have to define the class, okay? And also for every class, we have to define some constructor, right? We have to define some constructor, okay? Okay, and we have to involve some method, okay? This is the definition of class, okay, in standard Python. And in constructor, the thing happened is it is executed once when your class is initialized, okay? When new instance is initialized, this constructor is called, right? And samely in here, this init is rolled as the constructor, and they are called once when this instance new architecture is made, okay? And we normally write some network initialization part here because when these new architectures are made, this network initialization, the structure definition had to be called, right? So in this initialization part, we normally define our structure and the weight initialization, okay? And here we have the forward function, forward method, and this is actually for implementing the forward rule, okay? And also we have to define maybe the backward rule and parameter update rule as the method when we do not use Pytorch library, right? We have to define these two by ourselves, but in Pytorch, this backward function is already implemented in the root functions, okay? So actually this class is inherit some Pytorch function, Pytorch class. So we actually inherit this backward function from the upper class, okay? So we don't have to, and also this backward function is, as I explained, this is implementing the numerical, calculating the gradient in the numerical way, and they are actually same for every forward function. So we can just inherit that, okay? We don't have to change them, okay? For the parameter update rule, it's same, okay? So we don't have to even implement backward function and parameter update rule, okay? But we have to define only the forward function, okay? So when implementing CNN architecture, the thing you have to do is two things. Filling these two blanks, okay? The network initialization part and also the forward functions, okay? And that looks like this here. Here you will define some layers inside the CNN. And the first part, self-start layer, you can see they are composed of conv2d, mainly conv2d operation, and composed of some of the ReLU layers and max pooling layers, okay? This is the former part of the CNN, right? And later part, the FC layer that is composed of multiple linear and ReLU layers. Actually, this part are similar to MLPs, okay? And your forward function, the thing you have to define is, given X, how to propagate the signals, okay? First, you will input X to self-star layer you define here, right? The former part here. This is the self-star layer. You will first apply your input X to self-star layer, and then this is the flattening code. You flatten that, and you will also input it to FC layer, and you will return the final output. So you have to define these two things, the network structure and the forward rule. Then you don't have to implement the backward or parameter update rule because it is inherited from the upper class, okay? And you will use the same training code, okay? The thing you have to change is this part, okay? So this class name is myCNN. You can initialize the network using this myCNN function, okay? And actually the later part we will learn from next Wednesday, not next, this Wednesday, okay? Let's finish here. Thank you.